Chapter 1, Infrared Absorption Spectroscopy. Introduction. Infrared absorption spectroscopy concerns the absorption of radiation in the infrared range and is probably the single most widely used method for investigating the structure of organic substance. The instrument used for recording the infrared spectroscopy is known as infrared spectrophotometer. The infrared region of electromagnetic spectrum ranges from 0.8 to 200 UM, but most of the infrared spectrophotometer have a range of 2.5 UM to 17.2 UM. The infrared region between 0.8 and 2.5 UM is generally known as near infrared, and that between 15 and 200 UM is known as far infrared region. Since the organic molecule rarely undergo absorption of radiation in the near and far infrared region, these are seldom used for spectroscopic purpose. The various absorption band in an infrared spectrum are referred to either by the wavelength or wave number of the radiation absorbed. Band intensity is expressed in terms of absorbance or transmittance, the two being related to each other as A is equal to log 1 upon T. Basic theory of IR spectroscopy: molecular vibration. The atom constituting a molecule are not held rigidly in fixed position. They are continuously rotating and vibrating in number of ways. To have an idea of molecular vibration, let us compare a band between two atoms in a molecule to a weightless spring connecting two balls together. Just as the spring can be compressed and stretched or bent, the bond can be stretched or bent, giving rise to vibration in a molecule. There are two main kinds of molecular vibration. These are stretching vibration, bending vibration. Stretching vibration or bond stretching. In a simple diatomic molecule AB, the only vibration which can occur in a rhythmic compression and extension along the AB bond. This type of periodic back and forth movement of atom along the covalent bond axis, which can be compared to that of a coiled spring, is known as stretching vibration or bond stretching. Type of stretching vibration: in triatomic or higher molecule, the stretching vibration can be of two types: symmetrical stretching. It is the stretching vibration in which the movement of atom with respect to the bond in the molecule is in the same direction. In other words, all the bonds to the atom are either stretched or compressed simultaneously. Asymmetrical stretching: it is the stretching vibration in which one atom moves toward the central atom while the other moves away from it. In other words, one bond is being stretched and the other is being compressed. Bending vibration or deformation: in triatomic and higher molecule, there can be another type of vibration involving change of bond angle. Such vibrational movements are referred to as bending vibration or deformation. Bending vibration may be defined as periodic change in bond angle between bonds formed by two atoms. Type of bending vibration: bending vibration can be of four types. Scissoring: this is an in-plane bending vibration in which two atoms move toward each other. Second, rocking: this is an in-plane bending vibration in which the two atoms move in the same direction. Third, wagging: it is an out-of-plane bending vibration in which the two atoms move simultaneously either above or below the plane with respect to the central atom. Fourth, twisting: this is an out-of-plane bending vibration in which one atom moves above the plane while the other moves down the plane with respect to central atom. Scissoring and rocking represent in-plane bending, while wagging and twisting represent out-of-plane bending. The different type of vibration in which a molecule are very important for structure determination by infrared method. It may be noted that bending vibration require less energy than stretching vibration because it is easier to bend a bond than to stretch it. Principle of IR spectroscopy: we know that atoms constituting a molecule are not held rigidly in fixed position. They are continuously rotating and vibrating in a number of ways. The various methods of vibration possible in a molecule depend primarily on the nature of bonds themselves and to some extent on the nature of the entire molecule. Absorption of infrared radiation by a bond increase the amplitude of vibration and also bring change in rotational energy level. However, in the infrared range usually studied, the absorbed energy bring about predominant change in the vibrational energy level. It is obvious that the given bond or a part of molecule can absorb only that wavelength of infrared radiation which will provide the photon of that particular amount of energy which is required to raise the vibrational energy level to a permitted value. As the infrared radiation of a specific wavelength is absorbed, an absorption signal is produced. Thus, infrared spectroscopy is based upon the absorption of infrared radiation by the molecule in accordance with the quantization of their vibrational energy level. The record of amount of infrared radiation of different wavelengths absorbed to raise the vibrational energy level constitute the infrared spectrum of the molecule. Some of the stretching and bending vibration possible for an alcohol group and the characteristics wavelength absorption due to these vibration. A wavelength range is given for each of these vibration because the actual value will also be determined by the nature of rest of the molecule. Unit in IR spectroscopy. The position of absorption of infrared radiation in IR spectroscopy is generally expressed in terms of wavelength or in terms of wave number in centimeter inverse. However, the wave number is usually treated as absorption band frequency. The wave number corresponding to wavelength of the infrared range usually studied are from 4000 centimeter inverse to 667 centimeter inverse. Calculation of vibrational frequency Hooke's law. The molecule of an organic compound usually contain many carbon and carbon hydrogen bond and also some other bond. Therefore, the analysis of various bond of vibration for a molecule is very difficult because all the atoms present in the molecule contribute to the vibrational mode. However, it is still possible to calculate approximately where a particular vibration mode will appear in the infrared spectrum by considering each bond present in the molecule one at a time and ignoring the other bond. Let us, for instance, consider the stretching vibration of two bonded atoms. The stretching vibration can be compared to the oscillation of two balls connected by a spring, where the balls represent the atom and the spring represent the bond. As such, the value of stretching vibration frequency of the bond can be calculated fairly accurately by the application of Hooke's law, which may be represented as V is equal to 1 by 2 pi under the root k by mu, where k is called the force constant which is related to the strength of bond. U is termed the reduced mass of the diatomic system. It is calculated from the expression mu is equal to m1 into m2 upon m1 plus m2, where m1 and m2 are the actual masses of two atoms in gram. Factors which determine the vibration frequency. The simple analogy between the two bonded atoms and a simple oscillator help us in knowing the frequency of various absorption band in the infrared spectrum from the nature of atom and strength of bond between them as illustrated below. The smaller the mass of bonded atom, the smaller is the reduced mass and therefore higher the vibrational frequency. In other words, vibrational frequency is inversely proportional to reduced mass. The bond between hydrogen and other atom have the highest known fundamental frequency, but covalent compound of halogen or most metals shown infrared absorption of very low frequency, which are too low to be recorded on a routine spectrophotometer. The force constant is a measure of strength of bond and therefore its value increase with the increase in bond order. It is taken as approximately 5 into 10 raised to power 5 dynes centimeter inverse for a single bond between any two atoms. For double and triple bond, the value are 10 into 10 raised to power 5 and 15 into 10 raised to power 5 dynes centimeter inverse respectively. With the increase in the value of K corresponding to the increase in bond strength, vibrational frequency also increases. In other words, vibrational frequency is directly proportional to bond strength. It must be noted, however, that the intensity of absorption depends mainly on the polarity of the bond. Number of fundamental vibration. It has been stated earlier that absorption of infrared radiation having energy equal to the difference between two vibration energy level will lead to a vibrational transition. In the transition from ground state to first excited state, Light is absorbed strongly, and as a result, intense band called fundamental absorption band are produced. The number of fundamental absorption band exhibited by a molecule is related to the fundamental ways of vibration or vibrational mode available to a molecule. In general, number of fundamental absorption band is equal to number of fundamental vibrational mode. Since a diatomic molecule has only one fundamental vibration mode, it will give rise to one fundamental absorption band. However, polyatomic molecule can have more than one kind of vibrational movement. They exhibit more than one fundamental absorption band as given below. Non-linear polyatomic molecule. It has been found that non-linear polyatomic molecule can have 3 and minus 6 mode of fundamental vibration, where n is the number of atoms present in the molecule. For example, water, n is equal to 3 has 3 vibrational modes, each of which can give an absorption band. Linear polyatomic molecule. Linear polyatomic molecule having n atom can have 3 and minus 5 fundamental vibration. For example, carbon dioxide n is equal to 3 has 4 vibrational mode. In case of larger molecules, the number of fundamental vibration goes on increasing very rapidly with the increase in the value of n, but it has been observed that the number of fundamental band actually obtained is usually less than the expected from the theoretical number of fundamental vibration. This may be due to following reason. Some of the fundamental vibration may be very weak and therefore may not be recorded as band. Some of the fundamental vibration may be very close, and as a result overlapping of band may take place. Some of the fundamental vibration may involve energy change which fall outside of usual IR range. It is also interesting to note that sometimes additional bands such as combination band, difference band and overton may also be exhibited. Selection rule. Most of the molecule possesses dipole moment due to presence of polar bond linking the constituent atom. When a polar bond undergoes stretching vibration along the internuclear axis, a change in electron distribution of the bond takes place. As a result, dipole moment also undergo a change. In other words, a vibration produces a fluctuating dipole moment. Interaction between the oscillating dipole moment and the infrared radiation lead to the absorption of energy from the radiation so that the energy of vibration increase. This interaction and absorption of energy can occur only if the dipole moment at one extreme of the vibration is different from the dipole moment at the other extreme of the vibration in a molecule. It is evident from the above discussion that a bond vibration can lead to absorption of infrared radiation only if it is accompanied by a change of dipole moment. As a result of comprehensive studies in the field of spectroscopy, certain generalizations have been made which determine whether a vibration would be effective for a particular type of spectrum or not. These are known as selection rule. For infrared spectrum, the rule is that only those vibrations are effective in causing absorption which are not centrosymmetric. For example, symmetric stretching vibration of CO2 are centrosymmetric and are not effective in infrared spectroscopy, while the asymmetric stretching vibrations are not centrosymmetric and give rise to absorption spectroscopy. In infrared region, since most of the functional group in organic chemistry such as C double bond OH and NH undergo vibration which are not centrosymmetry, they respond very well to infrared spectroscopy. Position and intensity of band. Depending upon the type of bond present in a molecule, various wavelengths are found to be absorbed in the infrared spectrum of the molecule, giving rise to absorption band. The position of particular bond or group indicate the presence of that bond or group in the molecule. For instance, presence in the spectrum recorded, the absorption band at 3 um clearly established the presence of a hydroxyl group in the molecule. Similarly, the absorption of characteristic absorption band of a bond or group guarantees the absence of that particular bond or group. It may be noted, however, The actual absorption pattern of a band or group may vary slightly from one type of molecule to another. This is because of the exact position of absorption band is also determined to a very small extent by the nature of rest of the molecule. Infrared spectrum can be usually divided into two regions for the purpose of its interpretation. First, functional group region in a general absorption band from 2.5 to 8 are associated with the change in the vibrational state of the various bonds. Accordingly, this region is characteristic of the type of bond present and may be termed as functional group region of the infrared spectrum. Fingerprint region. Absorption band in the region 8 are generally associated with complex vibrational and rotational energy change of the molecule as a whole. This region is very useful for establishing whether two compounds are identical or different from each other. It is therefore referred to as the fingerprint region. There are so many absorption bands in the fingerprint region that no two compounds, however closely related, can have identical IR spectrum in all detail including intensity. On the other hand, can it if two given samples have exactly the same infrared spectrum, it is a conclusive proof of the identity of two samples. Intensity of absorption band. Different absorption band in infrared spectrum have different intensity. The intensity of absorption band is mainly depend on the magnitude of change in dipole moment. The more the polar character of a bond, the greater the change in dipole moment, the greater the intensity of absorption. For example, a carbonyl group has a much higher dipole moment than carbon double bond carbon, and therefore it gives rise to stretching absorption band of much higher intensity than carbon double bond carbon stretching absorption band. The intensity of absorption band also increased to a smaller extent with the increase in the concentration of molecule in the sample and the number of absorbing group in a molecule. Factor influencing vibrational frequency. We have seen that the probable frequency of a bond in its IR spectrum can be calculated with the help of Hooke's law. However, it has been found that the calculated value for a bond is only in tolerable agreement with the experimental value but never equal to it. This is because the vibration of each group is influenced by the structure of the rest of other molecule in its immediate neighborhood. The important factor responsible for vibrational shift are as follows. First, electronic factor. When the substituent in the neighborhood of a particular group are changed, it brings about change in the absorption frequency of that group due to electronic effect, such as inductive effect and resonance effect. Due to these effects, the force constant or bond strength change which cause the absorption frequency shift from its normal value. Inductive effect. The presence of alkyl group in the vicinity of a particular group cause plus I effect. As a result, the bond length of that group tend to increase or the bond strength decrease. Consequently, the force constant is lowered and the frequency or wave number of absorption decrease. This is clear from the following example showing the absorption wave number of carbonyl group in different compound. It is obvious that greater the plus I effect, smaller the wave number. It if on the other hand a group having minus I effect is present in the neighborhood of a particular group, it increases the value of force constant. As a result, the absorption shift to a higher wave number as shown below in term of absorption wave number of carbonyl group in acetone, chloroacetone and dichloroacetone. It is apparent that greater the minus I effect, higher is the wave number. Second, resonance effect. Resonance effect has significant influence on the absorption frequencies in the infrared spectra of many compounds. For instance, conjugation lower the absorption frequency or wave number of ethylenic bond in conjugated diene and of the carbonyl group in conjugation with ethylenic bond or aromatic ring. This is because conjugation tend to increase the bond length of the group so that its bond strength decrease. This in turn lowered the force constant of the bond and the absorption frequency decrease. This is evident from the absorption frequency of carbon double bond oxygen stretching in the following compound. Second, hydrogen bonding. This infrared spectra of organic compounds such as alcohol, phenol, carboxylic acid, and amine which exhibit hydrogen bonding are strongly influenced by the presence of hydrogen bonding. Hydrogen bonding results in the weakening of bond involved so that the force constant decrease and the absorption shift toward lower frequency or wave number. Some important generalization about the role of hydrogen bonding in infrared spectroscopy are as follow. The stronger the hydrogen bonding, the greater the downward shift in the absorption frequency. Intermolecular hydrogen bonding give rise to broader band, while intramolecular hydrogen bonding give rise to sharp and well-defined band. The intensity of absorption band in intermolecular hydrogen bonding is concentration dependent and decrease with dilution. In concentration has no effect on the intensity in case of intramolecular hydrogen bonding because it takes place within the same molecule. The downward shift is more pronounced in case of intermolecular hydrogen bonding than in intramolecular hydrogen bonding. Let's illustrate the above generalization with some example. Alcohol and phenol. In case of both alcohol and phenol, the free OH group give rise to strong absorption band in the region 3650 to 3600 centimeter inverse. On the other hand, hydrogen bonded OH group give broad absorption band in the region 3400 to 3200 centimeter inverse. Carboxylic acid. Carboxylic acid generally exists as dimer having strong intermolecular hydrogen bond. Due to large strength of hydrogen bond, there is large decrease in absorption frequency of carbon double bond oxygen and OH stretching frequency in these dimer. Thus, carboxylic acid dimer exhibit a very broad band due to OH stretching at 3000 to 2500 centimeter inverse. Similarly, there is downward shift for carbon double bond oxygen stretching in acid from about 1750 centimeter inverse to about 1700 centimeter inverse. Amines. Due to relatively weaker hydrogen bonding in amine, the downward shift in the absorption frequency of NH bond is only from about 3500 centimeter inverse to about 3300 centimeter inverse. This is much lesser than in case of OH bond in alcohol and carboxylic acid. Third, vibrational coupling. It has been observed that in some group containing two or more similar atoms bonded to a central atom, the absorption frequency of a band is different from that of the isolated bond of the same type. This is due to mechanical interaction between the stretching vibration of the bond known as vibrational coupling. For example, an isolated CH bond has only one stretching frequency, but a CH2 group which has two carbon hydrogen bond involving a common carbon atom showing two absorption frequency, each of which occur at different value as compared to isolated CH bond. This is because the stretching vibration of two CH bond in CH2 interact with each other in two different ways, asymmetric stretching and symmetric stretching, to give rise to coupled vibration. Due to asymmetric stretching, the absorption takes place at higher wave number, while symmetrical stretching shifts the absorption to lower wave number than the isolated bond. Similarly, a CH3 group, NH2 group, NO2 group, and carboxylate ion show coupled vibration due to asymmetric and symmetric vibration stretching. Instrumentation mechanic of recording the IR spectra. In an infrared spectrophotometer, the sample of substance under investigation is placed in a beam of infrared radiation. The relative intensity of transmitted and therefore absorbed radiation is automatically measured and plotted on a graph, showing intensity of transmission or absorption as a function of wavelength or frequency of infrared radiation. Monochromator. By means of prism or diffraction grating, the monochromator allows radiation of only one frequency to enter the detector at a time. The frequency of radiation get automatically varied. Detector. The detector scans the range of infrared frequency received from the monochromator and transforms the energy of the radiation received in an electrical signal. This signal is proportional to the difference in the intensity of radiation in the sample and reference beam. Characteristic absorption region of various bond. The characteristic infrared absorption region of various type of bond and functional group are collected in the form of tables called correlation table. Table 1.1 is the correlation of data on absorbed pattern of same important bond and functional group. The letter S, M, W, V denote whether the intensity of absorption is strong, moderate, weak, or variable. It should be remembered, however, that the table gives only the approximate position of absorption band, but the already stated the exact position of absorbed band of a particular bond depend upon its actual molecular environment. Spectral feature of some classes of compound. Having discussed the functional fundamental concept of infrared spectroscopy in the previous section, we now take up the spectral feature of some classes of compound. Hydrocarbon. First, alkene. Infrared spectra of alkene are generally quite simple and not very informative because alkene do not contain any functional group. The most common peak exhibited by alkene are given below. CH3, CH2 and CH group present in alkene give rise to CH stretching absorption band in the region 2960 to 2850 centimeter inverse. CH3 and CH2 also exhibit bending or deformation band in the region 1470 to 1430 centimeter inverse. CC bone are less characteristic and they are responsible for weak bond in the region 1300 to 800 centimeter inverse. Second, alkene. Infrared spectra of alkene show many characteristic absorption which can be very useful in structural determination. The most prominent peak in the vinylic stretching at slightly greater than 3000 centimeters inverse. The actual position depending upon the extent of substitution in alkene. Carbon double bond carbon stretching vibration give rise to band of variable intensity at 1680 to 1620 centimeter inverse. Conjugation shift the position to lower frequency and increase the intensity of absorption. Third, alkyne. They exhibit strong absorption band for CH stretching near 3300 centimeter inverse and another intense bond CH bending at 650 to 610 centimeter inverse. AV carbon triple bond carbon stretching absorption band occur at 2100 to 2260 centimeter inverse. The band is more intense for terminal alkyne than non-terminal alkyne. Fourth, cycloalkane. Cycloalkane exhibit mainly CH stretching absorption band. The reason of absorption move to higher value with the increase in angle strain. For example, CH stretching for cyclopropane is at 3050 centimeter inverse, while that for cyclohexane is at 2990 centimeter inverse. Aromatic hydrocarbon. These compound exhibit CH stretching absorption at 3050 to 3000 centimeter inverse and CH stretching absorption at 1600 to 1450 centimeter inverse. There are four prominent stretching band at 1600, 1580, 1500 and 1450 centimeter inverse. Absence of these band means that the compound is not aromatic. There are also a number of CH bending band at 900 to 700 centimeter inverse. The actual number and position of these band depend upon the extent and position of substitution of aromatic ring. Hydroxy compound. Alcohol. The OH functional group of alcohol give a characteristic OH stretching absorption band in the infrared spectrum, but as we might expect, these absorption are significantly influenced by hydrogen bonding. If there is no hydrogen bonding, an alcohol give a sharp variable band at 3640 to 3610 centimeter inverse. In the associated state involving intermolecular hydrogen bonding, a strong broad band appear at 3400 to 3200 centimeter inverse. In case of intramolecular hydrogen bonding, the OH stretching band appear at 3570 to 3450 centimeter inverse and is of variable intensity. In addition, alcohol also exhibit a strong and broad band in the range 1200 to 1000 centimeter inverse. due to CO stretching. The exact location of band depend upon whether the alcohol is primary, secondary or tertiary. Therefore, it can be used to determine the class of alcohol. The complete spectrum of alcohol of course exhibit other absorption band as well as due to presence of other structural units such as carbon, single bond carbon and carbon hydrogen bond. This is quite evident from the higher spectrum of ethyl alcohol shown. Phenol, as in case of alcohol, phenol exhibit a strong band due to OH stretching in the range 3600 to 3200 cm inverse. However, the CO stretching band in phenol appear in a higher region as compared with alcohol. Ether, the infrared spectra of ether are characterized by strong absorption band in the region 1300 to 1000 cm inverse due to CH stretching vibration. Alkyl ether show a single absorption in the region 1150 to 1060 cm inverse. Aryl and vinyl ether exhibit a strong band in the region 1275 to 1200 cm inverse and a weaker band in the region 1200 to 1075 cm inverse. The CO stretching absorption band of ether are similar to those of alcohol, carboxylic acid, and ester. However, ether can be distinguished from alcohol by the absence of OH bond stretching at 3600 to 3200 cm inverse. Similarly, ether can be distinguished from carboxylic acid and ester by the absence of C double bond O stretching absorption at 1770 to 1680 cm inverse. Aldehyde and ketone. The infrared spectra of aldehyde and ketone are extremely useful in determining the presence of these compounds. The carbonyl group in these classes of compounds show a strong carbon double bond oxygen stretching band around 1700 cm inwards. The actual position of band depending upon the nature of group attached to the carbonyl group. Aldehyde. The position of carbon double bond oxygen stretching absorption band in aldehyde varies slightly according to the aldehyde is a saturated aliphatic aldehyde or aromatic aldehyde or alpha beta unsaturated aldehyde. Further, the presence of electron releasing group shift the absorption to lower value while the electron attracting group shift the absorption to higher value. In addition to carbon double bond oxygen stretching band, aldehyde show characteristic carbon hydrogen stretching band near 2820 cm inverse and 2720 cm inverse. Generally, the band near 2720 cm inverse is seen and it is a very useful in distinguishing aldehyde and ketone. Ketone. The carbon double bond oxygen stretching band in ketone appear at lower frequency or wave number as compared to aldehyde due to the larger plus I effect operating in ketone. The carbon double bond oxygen stretching absorption take place at still lower value for aromatic ketone and alpha beta unsaturated ketone. In case of cycloalkanones, the position of the carbon double bond oxygen stretching band depend upon the size of the ring. As the size of the ring decrease, the absorption shift to higher value due to increase in angle strain. It must be emphasized that carbon double bond oxygen stretching band is also given by carboxylic acid and their derivative. However, these compounds also show certain other band which help to distinguish them from aldehyde and ketone. For example, carboxylic acid also show a broad OH band in the region 300 3000 to 2500 centimeter inverse in addition to the carbonyl band. Carboxylic acid. The infrared absorption spectra of carboxylic acid exhibit a number of absorption bands which are very helpful in the detection of carbon double bond H C double OH functional group. This there is a very broad and intense band in 3000 to 2500 centimeter inverse range due to OH stretching. This is clearly indicative of strong hydrogen bonding than in alcohol where the OH stretching band is in the region of 3600 to 3200 centimeter inverse. Another strong band appear around 1700 centimeter inverse due to carbon double bond oxygen stretching. In addition, carboxylic acid also show a carbon-oxygen stretching band at about 1250 centimeter inverse and a bending band for OH near 1400 centimeter inverse and 920 centimeter inverse. Carboxylic acid derivative. Carboxylic acid derivatives. As expected, the infrared spectra of acid derivative are characterized by presence of strong C double bond O stretching band. The exact frequency of the band depending upon the nature of the compound. Thus, acid chloride show a strong band at 1815 to 1785 centimeter inverse, while acid anhydride exhibit two strong band at 1840 to 1800 centimeter inverse and 1780 to 1740 centimeter inverse. However, in conjugated acid chloride and anhydride, these bands occur at 15 to 20 centimeter inverse lower frequency. Amide show carbon double bond oxygen stretching band at 1690 to 1650 centimeter inverse. Saturated aliphatic ester give the carbon double bond oxygen band around 1740 centimeter inverse. Alpha beta unsaturated ester and aryl ester exhibit this band at 1730 to 1715 centimeter inverse, while vinylic ester and phenylic ester show this band around 1770 centimeter inverse. Ester and anhydride also give two strong carbon oxygen stretching band in the region 1350 to 1050 centimeter inverse. This serves to distinguish them from ketones. Acid chloride show carbon chlorine stretching band in the 800 to 650 centimeter inverse range. Amide show NH stretching band at 3500 to 3100 centimeter inverse and also NH bending band around 1600 centimeter inverse. Unlike carboxylic acid, acid derivative do not give any broad OH stretching band. Amines. The infrared spectra of amines show characteristic absorption band due to NH stretching, NH bending, and CN stretching. The number and position of band depend upon the class to which the amine belongs. Primary and secondary amine exhibit moderately weak absorption at 3500 to 3200 centimeter inverse due to NH stretching vibration. However, primary amine have two such band in this region, while secondary amine show only one band. Tertiary amine do not have any NH band in their molecule and therefore they do not exhibit such band. Hydrogen bonding tend to shift the NH band to lower frequency, but the shift is not as much as in case of hydroxyl compound. This is because the hydrogen bonding in amine is weaker than that in hydroxyl compound. Primary amine exhibit moderately strong NH bending band at 1650 to 1560 centimeter inverse and 900 to 650 centimeter inverse, while secondary amine show weak band of this type around 1600 to 1500 centimeter inverse. The CN stretching band of aliphatic amine appear in the region 1230 to 1030 centimeter inverse. The intensity of absorption being weak, on the other hand, may be you on the other hand, aromatic amine exhibit two strong band at 1360 to 1180 centimeter inverse due to CN stretching. These bands may be used to distinguish between aliphatic and aromatic amine. The salt of amines such as hydrochloride show a broad band in the 3000 to 2200 centimeter inverse region, which is typical of ammonium ion. The main feature of infrared spectra of amine are given in table 1.11. Nitrile. The infrared spectra of nitrile are characterized by presence of carbon triple moon and stretching absorption band at 2260 to 2220 centimeter inverse of variable intensity. Conjugation with double bond or aromatic ring shift the absorption to lower frequency. Nitro compound. The infrared spectra of nitro compound show two strong band at about 1560 centimeter inverse and 1350 centimeter inverse due to symmetrical and asymmetrical stretching of N double bond O bond. Primary nitro compound absorb at higher frequency as compared to secondary, while tertiary compound absorb at even lower frequency. Conjugation of nitro group with an aromatic ring move these band to lower frequencies. For example, nitrobenzene show absorption band at 1525 centimeter inverse and 1350 centimeter inverse. Interpretation of IR spectra. Having studied the characteristic absorption position of various functional groups, we give below a few useful tips for remembering the specific absorption region and interpreting the infrared spectra. Remembering the specific absorption region. For this purpose, the infrared range from 4000 to 700 centimeter inverse may be broadly treated as consisting of four parts. The region from 4000 to 2500 centimeter inverse is the absorption region of carbon hydrogen OH and NH single bond stretching vibration. NH and OH bond absorb in the region 3300 to 3600 centimeter inverse, while CH bond absorption occurs around 3000 centimeter inverse. The region from 2500 to 2000 centimeter inverse correspond to carbon triple bond carbon and carbon triple bond nitrogen stretching absorption. The region from 2000 to 1500 centimeter inverse deal with carbon double bond carbon, carbon double bond oxygen and carbon double bond nitrogen double bond stretching vibration. Carbonyl group generally absorb between 1670 to 1780 centimeter inverse, while ethylenic double bond absorption generally take place from 1640 to 1680 centimeter inverse. The region below 1500 centimeter inverse constitute the fingerprint region where a number of complex absorption band appear due to different kind of carbon single bond carbon, carbon single bond oxygen, carbon single bond nitrogen and carbon single bond halogen single bond vibration. Interpreting the infrared spectrum. The following points should prove very helpful in the interpretation of infrared spectrum. Always start with the high frequency end of the spectrum. The absorption band due to most of the stretching vibration appear in the region below 1500 centimeter inverse. The region below 1500 centimeter inverse is used only for the confirmation of the identity of compound. It is neither necessary nor possible to interpret each and every absorption band. Most of the information is obtained from a relatively few bands. The negative evidence is always more reliable. What this statement means is that the absence of a characteristic absorption band of a bond or group is sure guarantee of the absence of that particular bond or group. For example, if there is no absorption band in the region 1600 to 1800 centimeter inverse, the carbonyl group must be absent in the compound. Overton and coupling peaks. Before concluding this discussion, it may be pointed out that the actual appearance of IR spectrum because become rather complicated due to absence appearance of certain absorption band in addition to the band due to fundamental vibrational mode of various mode. Such as additional band are called overtones and coupling peak, but these additional band are much less intense than fundamental band overtones. These are high frequency band which may occur at or near integral multiple of the fundamental band frequency. Fermi resonance. Usually the overtone and combination band are much less intense than the fundamental band. But if the energy of fundamental vibration is quite close to that of an overtone or combination band, energy is transferred from the fundamental vibration to the additional vibration. This increases the intensity of overtone or combination band. This mechanical coupling between fundamental band and additional band is known as Fermi resonance. This is quite often observed in the IR spectra of carbonyl compound, IR spectra of some simple molecule. As practical illustration of interpretation if IR spectra, let us now identify the significant absorption band in the spectra of some simple molecule. IR spectra of acetic acid. The important band in the above spectra are as follows: 3030 centimeter inverse, a broad band of hydrogen bonded or stretching of a carboxylic acid, 1710 centimeter inverse, C double bond or stretching of a saturated chain carboxylic acid, 1280 centimeter inverse, CO stretching of a carboxylic acid, 945 centimeter inverse OH bending of a carboxylic acid. IR spectra of benzaldehyde. Application of infrared spectroscopy. The infrared spectrum is a highly characteristic property of a substance, and the examination of infrared spectrum can aid chemical investigation in many ways. The important application of infrared spectroscopy are as follows. Identification of substance. Infrared spectroscopy is very often used to establish whether a given sample of an organic substance is identical with another or not. Due to large number of absorption band found in the infrared spectra of organic compound, the probability that any two compound will produce identical spectra is practically zero. This means that if two samples afford identical spectra under similar condition of measurement, they must be sample of the same substance. However, the condition of recording the spectra, such as physical state of sample, solvent used as concentration of solution must be the same because a substance may produce appreciably different spectra under different set of conditions. It may be noted that the infrared spectra of two enantiomeric compounds taken under the same condition are exactly identical. In other words, infrared spectroscopy fails to distinguish between enantiomer, determination of functional group, and molecular structure. Infrared spectroscopy is very helpful in determining the molecular structure of unknown substance from an examination of the position of absorption band in the spectrum. It is often possible to establish the nature of group present in the molecule. For example, if a spectrum contains a strong band at 5.82 um, the compound concerned must contain a carbonyl group. This information, in conjunction with the study of other bands, may tell a great deal about the structure of the compound. It is obvious that if a structure spectrum does not contain an absorption band typical of a particular functional group, substance does not contain that group. Studying the progress of reaction. Progress of a chemical reaction can be readily followed by examining spectra of small portion of reaction mixture withdraw from time to time. The rate of disappearance of a characteristic absorption band of a reactant group of the rate of increasing absorption band due to formation of some product help in studying of a reactant group or the rate of increasing absorption band due to formation of some product help in studying the progress of the reaction. For example, the gradual disappearance of hydroxyl stretching frequency at 2.74 to 2.78 um and the consequent appearance of carbonyl stretching frequency at 5.68 to 5.95 can be used to study the oxidation of an alcohol to a carbonyl compound. Similarly, the systematic interpretation of IR spectrum can be very useful in determining whether a reaction has occurred to given give the expected product or not. Detection of impurities. It is possible to determine whether a given sample of a compound is pure or not, provided the reference spectrum of pure compound is available. In contrast with the spectrum of the pure compound, the spectrum of an impure sample is blurred and not so sharp and contain many extra bands. For example, the presence of a ketone as an impurity in an alcohol lead to a rather poor spectrum having additional absorption band due to the carbonyl group. Some example of the use of infrared spectroscopy. To illustrate the use of infrared spectroscopy in structural analysis, a few simple examples are given below. Indicate the expected important absorption region in the IR spectra of the following compound: isopropyl alcohol, dimethyl ether, and toluene. Important absorption band expected in the IR spectrum of isopropylene alcohol are as follow: 3200 to 3400 cm inverse, a strong and broad band due to hydrogen bonded OH stretching. 2850 to 2950 cm inverse due to CH stretching. 1000 to 1300 cm inverse due to CO stretching. The important absorption band expected in the IR spectra of dimethyl ether: 1060 to 1100 to 50 cm inverse due to CO stretching. 2850 to 2950 cm inverse due to CS stretching of methyl group. The IR spectrum of toluene would be expected to have the following important absorption band: 2850 to 2950 cm inverse due to CS stretching of methyl group. 3000 to 3100 cm inverse due to CS stretching of aromatic ring. 1500 to 1600 cm inverse due to CH stretching of aromatic ring. Thank you.